So like I said, this is my first time to give such a lecture, so it will be far from being complete. But just consider it as trying to think out loud with you. I gathered some of relatively recent results that were not available to the early pioneers, and they don't seem to be well known to current fluid mechanics students either. Actually, I made this poll on my LinkedIn account about the vorticity generation mechanism at the wall, specifically the total amount of vorticity generated at the wall. And I asked it, does it depend strongly on viscosity or independent of viscosity? And as you can see, the majority believe that it's purely viscous. And in fact, some professors actually, they were very, very upset in their comments. It's like, why are we asking this? This is well established and obvious and well known, and you know. So I think, yeah, this is the main motivation of doing this lecture actually. Let me, just in case if I needed a pointer. All right, so let's, at the beginning I will try to bring some background from history that may shed light on why we came at this point, why we arrived at this point where many people believe in the value of viscosity. And actually the point may be related to this ubiquitous question of fluid mechanics, like if you have a solid moving into a fluid, how much force the fluid acts upon the solid, which is ubiquitous, we see it everywhere, right? And in fact, Lord Rayleigh, in his seminal paper on the resistance of fluid, he wrote this: there is no part of hydrodynamics more perplexing to the student than that which treats the resistance of fluids. And this question has baffled many scholars throughout the history. I'll have to start somewhere because of the time constraints. I'll have to start with Newton. I don't know why Newton didn't show up, but anyway, I should have a picture for Newton. He actually developed two theories. I will focus only on the second because it corrected the first, and both were wrong anyway. So in the second theory, a fluid flow, so he considered the fluid flow to be a continuous chain of particles, which they can move relative to each other, but unlike the first theory, the first theory he considered the fluid particles to have the ability to move independently of each other without affecting each other. Here he's saying, he came up with this expression, defectus lubricitatis, meaning lack of slipperiness, like two neighboring fluid particles, they cannot slip with respect to each other without affecting each other. So the slip velocity between two neighboring fluid particles has effect on their motion. He is basically alluding to viscosity kind of thing. And in proposition, here is the picture of Newton, came late. The proposition 34 of the Principia, Newton's main book, he actually managed to compute, based on this theory, he managed to compute the resistance on a cylinder. So a cylinder moving in a fluid, and he managed to compute this resistance moving with a speed u, cylinder radius r. Of course, they did not write like I'm writing now. If you go, you can see this in my lecture on history of fluid mechanics, part 1. You will see this in detail, how Newton, or at the time, they used to write this expression. I mean, they did not write in our notations. They write it in words, which is very interesting, and they relate it to gravity. So it's interesting to see it once in your life. So anyway, so that's the theory, and he did not apply it to flat plate, but if you consider this theory and try yourself to apply it to a flat plate, so here are a bunch of fluid particles moving, they're gonna impinge on the plate, losing their momentum component normal to the plate, resulting in normal force only, resulting in the famous sine square law. And if you use this, again, Newton did not write this sine square law, but it's very famous, it's coming from his theory. If you use this to get the lift component, here is the lift component out of it. This is CL versus alpha. The red is the Newtonian theory, basically R cosine alpha. And the black is the 2 pi alpha. You can see that it's way below, as people say, you know, nature turned out to be much more generous than what Newton had anticipated. In fact, some people say if this law were to be correct, aviation wouldn't be feasible because it's so little lift. It wouldn't make aviation possible, and in fact, very large drag. So in fact, some people even blame Newton for delaying aviation because, if people were interested in aviation and found his work, given his status, it might have discouraged them from pursuing aviation. But anyway, so what I'm trying to say here is that even Newton could not manage to answer this question, which is how much a force fluid exerts on a solid. And at the time, it was not Newton only. It was actually, I would describe it as a morass of theoretical results and experimental results that do not match each other. So when this kind of chaos, scientific chaos, was happening, the Academy of Berlin, they made a competition. They said, hey folks, we need to sit down and tell us how can we compute the resistance of fluid acting on solid. They mandated that the winning thesis or whatever must present both theoretical and experimental investigations, right, simultaneously. Of course, nobody could at the time, so there were no awards. We're talking about this is the best minds, perhaps in the modern history, right? This is the peak of the age of enlightenment. Newton, D'Alembert, blah blah blah. So anyway, D'Alembert participated, and he actually did not like this decision because he believed that the theoretical treatment of this problem is too complicated to allow for simultaneous experimental verification. But anyway, he did some theoretical studies and he collected them and published in this very famous paper where he tried to solve the flow over some shapes, and whenever he found completely symmetric flow fields fore, aft, up and down, resulting in zero net force. So he concluded with the famous conclusion, I must therefore confess that I do not know how the resistance of fluids can be explained by the theory in a satisfactory way. On the contrary, it seems to me that this theory, handled with all possible rigor, yields a resistance which is absolutely nothing, zero, in at least several situations. I bequeath this strange paradox to the geometers that they may explain. This is the D'Alembert paradox. So after this came Euler, with his amazing idea of amazing concept, a revolutionary concept of continuum fluid, in the sense that now he's treating with the fluid element. Yes, please, Thomas.
When D'Alembert did that, did they just not understand the idea of viscosity in general, or did they purposefully neglect these effects of viscosity when trying to come up with a theory?
There was no equation of motion that accounts for viscosity at the time. So even Euler equation was not available at the time. There was just force equal mass times acceleration. But how to apply force equal mass times acceleration is very generic. How to apply it on fluid? How to treat the fluid? So Newton actually treated the fluid as a bunch of particles. You'll see later. As we know, fluid mechanics. So Euler he came up with the concept of fluid element. So it's not just a particle moving. It's actually large enough so that we're not talking about molecular level, and small enough so that we can apply differential calculus. It's an invention by itself. So in fact you will see Lagrange describing Euler, he did not contribute to fluid mechanics but created it, which is really true. So Euler wrote two main papers to the Academy of Berlin, I guess. One on equilibrium of fluids, where he recovered the equations of equilibrium that were previously derived by D'Alembert and Clairaut. And then he did the second one, which is the most famous one. This is the one for motion. And was very generic, by the way. It was for compressible, non-homogeneous fluid. So this is where he derived this equation of motion, and it was crystal clear. This paper is, I'm not sure if it's available, but it's reproduced in René Dugas' book, History of Mechanics. He reproduced it. You can go and follow, and if you follow, you will find that it's as if you're reading a recent book. It's the same language. You will see a fluid element, P from one side, P plus dP from the other side, applying Newton's equations of motion and neglecting higher order terms. It's the exact same derivation we see in graduate school. And this is why Dugas actually described the clarity of this paper as So perfect is this paper that not a line has aged. It's interesting also to see this quote by Lagrange. By the discovery of Euler, the whole mechanics of fluids was reduced to a matter of analysis alone. Unfortunately, they are so difficult that up to the present, it has only been possible to succeed in very special cases. And when I read this, I actually I laugh because it's the same situation. Euler equations are available, but they are so difficult we cannot solve them in the general case. We can solve them in only special cases, perhaps the exact same special cases that they solved. I'm not sure, but it's the same situation 300 years after the discovery of the equation. But the derivation of Euler equation did not help much in the question that we had about the force. In fact, Couette had a nice comment on that. He said, Euler was the creator of hydrodynamics, but the beautiful trousers he tailored had no buttons. They failed to include viscosity. So then came Navier, as you guys know, and Navier wrote 3 famous papers to the Académie des Sciences, French Academy of Science, one on elasticity, one on hydrostatics, one on hydrodynamics. And you know, in fact, Navier did not follow the steps of Euler, the concept of continuum fluid mechanics, fluid element. Rather, he tackled, you know, molecules directly, what people refer to as molecular hypothesis. So he said, okay, I have a bunch of molecules, and there is a repulsive force between the molecules that depend only on the relative distance between the molecules. And from there, he applied Newton's equations of motion. So this is a completely different model than Euler continuum mechanics. And he derived the equation of motion for, like I said, there is elasticity, there is hydrostatics, equilibrium. In the case of hydrostatics, he recovered from a completely different perspective. There is no continuum. He recovered the exact same equations of motion. You know, I'm sorry, not equations of motion, equations of equilibrium that were derived previously by D'Alembert and also Euler in the case of equilibrium. With the following analogy, that our pressure term that we know appears in his equations as this term, which is a measure of the molecular force. So our pressure in Navier's equation is actually a measure of molecular forces. Then he did hydrodynamics, motion. He said in hydrodynamics, in the motion, there is an additional molecular force between molecules that is proportional to the relative speed between neighboring molecules. And when he derived his equations of motion, now his equations were Euler equations, look like Euler equations plus an additional term. And this additional term is exactly like our viscous term now that we know in Navier-Stokes equation, with the analogy that our viscosity appears in Navier's equation in this form. Again, it's a measure of the molecular force between molecules. So Navier never, you know, introduced friction explicitly. He was focused on the dynamics of molecules, and what we call as pressure and viscosity appear naturally as measures of these molecular forces. Okay. People did not like this hypothesis, did not like Navier's approach, did not touch the equations for about 25 years until Stokes came. Stokes, from the beginning, as you can see, from the title, from the get-go, I'm interested in the theory of internal flexion. So his focus, his main focus is, I want to capture the effect of friction. Like back to Thomas' question. So it's, we're fed up from analysis without friction, and perhaps this is the main cause why we're not getting consistent results. It's the time to include friction explicitly. And he followed Euler, concept of fluid element and continuum fluid mechanics. He derived the equations of motion. Interestingly, they turn out to be exactly the same equations of Navier with the analogy that we wrote here. All right. So the interesting part is that in the very next year, Prandtl published his report on his experimental data on the flow in capillary tubes, quantifying friction, relating it to the flow rate. And then afterwards, some people, including Helmholtz, they managed to recover the Prandtl law from Navier-Stokes equation. So that was the experimental, stamp. For the first time in the history of mechanics, we can compute resistance in fluids, right, in a systematic way from first principles. That's a big victory. So I personally believe that this moment is very important in the history of fluid mechanics, because before this moment, we could not really compute forces on bodies immersed in fluids. And after this moment, or at this moment, we managed for the first time to compute the force a fluid is acting on a solid. Why? What was the main enabler that allowed this to happen? Well, it's the Stokes equation, or Navier-Stokes equation. What was the unique term in Navier-Stokes equation that did not exist before? Well, it's the friction term. So this really set the mindset of people at the time that viscosity is so important in determining forces on objects. And any other trial that does not explicitly account for viscosity seem to be futile and fruitless from the outset, right? And you can see this more clearly in, let's say, land. We all have land. You can go and open it, and you will find this. It was, however, pointed out by Reynolds that the equations, meaning Navier-Stokes or Stokes, actually he referred to them as Stokes equations. Some people grant this victory to the British school because, like I said, when Navier came up with the equations, it was using a weird hypothesis. People didn't like it, and when Stokes came up with the exact same equations from crystal clear exposition, people sometimes attribute this victory to the British school. So Lamb belongs to the British school. So he's saying that these equations have been put to a very severe test in the experiments of Poiseuille and others. And then he followed, we can hardly hesitate to accept the equations as a complete statement of the laws of viscosity. So this is too much exaggeration. In fact, David Bloor, he commented that there is an immense authority behind this judgment. He's basically stamping this equation with a stamp of truth. He's saying complete statement of the laws of viscosity. I mean, that's too much to say. Particularly, in fact, I don't know what very severe tests he's talking about. Because Poiseuille experiments were for capillary tubes, right? This is very small speeds, very small dimensions, very small Reynolds numbers, laminar flow. So that's okay. Navier-Stokes works at laminar flow. Why on earth you claim that it will be successful in predicting turbulent flows at very high Reynolds number? There was no experiment. And even if there were experiments, we will not be able to solve Navier-Stokes itself. I need to solve Navier-Stokes, see the experiment and compare. At the time, there was no any capability to solve Navier-Stokes at very high Reynolds number turbulent flows, right? The very first, or one of the very first simulation, DNS simulation of Navier-Stokes at high Reynolds number was by Spallart in the late 80s. So this was a very early claim of victory by Lamb. But again, this gives you the kind of mindset at the community at the time that viscosity is so important to evaluate forces of, on solids. So this is why when we move forward and aviation happened and the Wright brothers flew their airplane, and at the time, as you guys know, there was no guiding principles or theory to answer even the simplest questions in aeronautic, like how much lift force is generated by a wing, for example. You can expect that the natural reaction by the British school is, well, any trial that does not explicitly account for viscosity would be futile and fruitless. This is why when Lanchester and the Germans, they developed the circulation theory of lift based on purely ideal fluid concepts, they were rejected in the British community, as we know from, for those who are interested, this is there is a video on the history of the theory of lift. I mean, many of you have watched it. So what were the arguments? I mean, you have seen these arguments, but I'm going to mention one of them just as a summary. So this is G.I. Taylor, great G.I. Taylor. So he wrote, Mr. Lanchester loses the possibility of generating the motion from a state of rest by a movement of the solid. So what does he mean? He means the following. Well, lift is due to circulation. Circulation is an integral of vorticity inside the boundary layer. Or it's an integral of vorticity in general over the area, right? But we know that in ideal fluids, vorticity cannot be generated or destroyed. You cannot create vorticity from nothing. That's an ideal fluid. That's the prevalent concept at the time. You cannot, and it's correct, right? I mean, There are these theorems by Helmholtz and others that, yeah, I mean, in ideal fluid, vorticity is conserved. In a different language, here in this class, we have dealt with the Kelvin circulation theorem. So again, in ideal fluids, the circulation is conserved. So if you have an airfoil, at the beginning, at the tarmac, the airplane is stationary, no flow. So please take a contour around the airfoil, there is no flow. So gamma is 0 of this contour. Now allow the airplane to move. Well, if this is ideal fluid, their concept at the time is that gamma is constant because of Kelvin circulation theory. So gamma will remain 0, so you will not be able to generate circulation over the airfoil. So as you can see from here, the main criticism was mainly about the mechanism of vorticity generation and circulation development. They did not see any mechanism in Inviscid fluid or purely ideal fluid to generate vorticity and circulation. That was the main issue. So this is actually the remaining of the lecture is all about the mechanism of vorticity and their generation. Any question before moving to explicitly to discuss the vorticity generation mechanism? Please, Varun.
Yeah, I'm wondering how did they solve like even a lambda case of Navier-Stokes equation without knowing what happens in the boundary layer?
Yeah, I mean these were
This is like 50 years before Prandtl discovered boundary layer. Right?
No, this is 1914.
No, I mean the code.
Oh yeah. Okay. No, this is there was no boundary layer there, right? This is because boundary layer we're talking about high enough Reynolds number. So there is a convective term. There is no convective term at all. These are the classical solutions you get in 230B.
Yeah.
You just neglect the convective term and you solve and you get a solution. It's valid for a very small Reynolds number. Yeah, so that's what they get. So this is why it's surprising why lambda is talking about high Reynolds number. So let's go to the vorticity generation mechanism and let's see what do classical textbooks, present. How they present it, the vorticity generation mechanism. So let's talk about Lighthill, one of the prominent fluid mechanicians. Section 1.5, solid boundaries as sources of vorticity. All right, let's read. The conclusion that a particle of fluid with zero vorticity will continue to have zero vorticity is false in a viscous fluid, since diffusion of vorticity from nearby particles can occur. So he's making it clear, you will not be able to acquire vorticity without viscosity. In the very next statement, he retorted, but diffusion cannot create vorticity out of nothing. This is Lighthill's words. So that in external aerodynamics, one may reasonably ask, when a uniform stream flow past on obstacles, how is vorticity imparted to the fluid, all of which lacks it initially? All right? Very clear. The answer, I'm quoting from Lighthill, the answer is that the solid boundary is a distributed source of vorticity. So he's saying basically, so here it's really clear, right? It's really clear that he's saying it's not diffusion. Diffusion cannot create fresh vorticity that did not exist before. He's saying it's the solid boundary. It's all coming from the boundary condition. And later, I mean, in the explanation, I highly recommend that you go, guys, and read this section. So he's saying, we now ask the question, how does a body moving through otherwise undisturbed fluid determine the development of the flow around it? This is the question that J.I. Taylor was asking. I mean, from a state of rest, right? So he explained, it's a long, I'm going to just summarize it. He's saying this, the answer is similar to how a computing machine could calculate how the flow field changes progressing by suitably small steps forward in time. So he's saying, let's talk about impulsive start. At time t equals 0, no effect of viscous diffusion whatsoever, because we're starting with an irrotational state, or zero everywhere, or free stream everywhere, so this term vanishes completely all over, right? So at time t equals 0, the viscous term provides no contribution. So he's saying compute the inviscid flow field using the no penetration boundary condition. And when you compute this inviscid flow field, as we know, if this is the wall, we will get some velocity distribution on the wall, tangential velocity distribution, which we think of currently as the edge of the boundary layer. That's why I denoted by U edge, all right? So he's saying the resulting tangential velocity at the surface may not satisfy the no-slip condition, of course. In this case, we deduce that exactly enough tangential vorticity must have been created at the surface so that the velocity field of that vorticity combines with that previously determined to give zero slip. He basically means that this edge velocity dictates the amount of vorticity inside the bound layer. This is exactly what he's saying. He said, once you have this tangential velocity, so this tangential velocity, we deduce exactly enough tangential vorticity inside the boundary layer to connect these two. And remember, the summation of all this is simply the U edge, right? So it's indeed the total amount of generated vorticity, according to Lighthill, has nothing to do with viscosity. It's just boundary condition. You know, this is the Inviscid. This is the Inviscid solution, right? U edge coming from the Inviscid solution. Any question about this before moving to the next slide?
But no slip condition.
Excellent. Yes. So this is why Lighthill said, yeah, no viscous diffusion at all has no effect, but it's the no slip boundary condition. We're coming back to this. So far, no viscosity, but the no slip boundary condition. Any question about that? So let's move forward. In fact, this is very famous. It's this mechanism to generate vorticity is very well known under the name Lighthill vorticity generation mechanism. All right.
So I just wanted to clarify.
Sure.
So like in boundary layer, we see that there is a long wall and we start from x equals 0. So basically Lighthill is saying that all the transport of boundary layer that we see down the line is due to viscosity, but the start of boundary layer.
What do you mean down the line? You mean along x?
Yeah, along x.
No, this U edge is along x. There's a velocity distribution along the wall. And at each section, this velocity distribution dictates the vorticity. In fact, Batchelor, here is another prominent fluid mechanician, and he also addressed this. Section 5.4, the source of vorticity in motions generated from rest. So this is now, I'm quoting from Batchelor, the first statement is mine. At t equals 0, again talking about impulsive start, an irrotational flow is developed, which, now I'm quoting, determined completely by the condition of zero flux of mass across the solid boundary. This is the no penetration boundary condition, has nothing to do with the no slip, right? It's an irrotational flow. And this unique irrotational motion almost inevitably has a non-zero tangential component of relative velocity of the fluid at the solid boundary, the U edge we talked about. Thus, the motion that would be generated from rest in the absence of diffusion of viscosity across the boundary of the fluid is accompanied by a non-zero tangential relative velocity at the boundary. Basically, that's the picture, right? So this is at time t equals 0, we have an irrotational motion everywhere, and this is the distribution on the boundary. U edge is determined completely from Inviscid considerations. And because of this difference, U edge here and immediately at the wall is 0 because of the no slip, right? So there is a jump. So this jump amounts to a little gamma that we know, or infinite sheet of vorticity. Again, here is Batchelor's own words. The vorticity in this flow is infinite at the boundary, right? Because it's concentrated. How much the vorticity integral? It's UE minus 0, right? But this much UE is distributed over a 0 thickness, so it's infinite. Okay, so this is why it's infinite. And then he wrote, this sheet of infinite vorticity at the boundary is the source from which, once viscosity is allowed to act, vorticity diffuses into the interior of the fluid, which is exactly this picture. All right? I mean, it can't be more clear than this. Any question about it? Again, so the integral of this is simply the U edge which is determined from outer flow consideration. And this is how we solve boundary layer, right? In order to go and solve the boundary layer equation, you need the boundary condition at the edge, basically, which is coming from Inviscid considerations. So in conclusion, Lighthill and Batchelor, they said it's not viscosity. It's clear. Any question here that it's not viscosity before moving to the next? And then just to make it clearer, they invoke the no slip. So this is not yet answered. Because some people said, yeah, the viscous term is useless. We agree. But the fact that you need the no slip, what physical mechanism that will enforce the no slip. It's viscosity, all right? So this is different. But let's now agree on this picture that it's not the viscous diffusion term at all, but they invoked the no slip boundary condition, both Batchelor and Lighthill. Any question about this? Abdurrahman.
In terms of evolution, if I want to see it as a source term in the evolution of vorticity, how can I formulate the no slip in that sense?
We will come back to it. We will, yeah, I mean, this is not the end. We will have examples and other things. And so let's see about the no slip. Let's move on. Actually, so that's the if this is what makes me a bit confused. If these are the classical textbooks,
I did not get the point completely where you said that on the boundary we have like UE to 0 but distributed over 0 bit. But like physically, like I have had discussions where we apply no slip assuming that the fluid came and a boundary of fluid got stuck to the boundary. And then like there is a gradient developing over. So
excellent. So yes, so indeed at time t equals 0, the no slip boundary condition is violated, even in the computational simulations of Navier-Stokes. Okay. Yes. So again, what I'm trying to say here is that I see that they made it very clear that the vorticity generation mechanism is not viscous. Yeah, there are discussions about the no slip, which makes me, a bit confused. I mean, these are the classical textbooks. So what is the main source behind the 77% of opinion that it's viscosity? There's something wrong going on. But anyway, let's move on. Then again, this was we're talking about 60s, okay, time frame, and even this picture was not available to G.I. Taylor. G.I. Taylor was not talking like this, right? He's saying, no, there is no way. You need viscous diffusion. This stuff was not available to the Lamb and G.I. Taylor, was not discussed at all in Lamb and the early pioneers. So this is a big step forward. It's not there yet. Why not there? Because they still invoke the no slip boundary condition. But here they made this term useless, the viscous diffusion. It's useless at all in generating fresh vorticity that did not exist before. So that was one step forward. The big leap was by Morton, 1984 paper. I highly recommend that every student in fluid mechanics should study this paper. And he was the first one to shout out loud and make it clear. This is the abstract of the paper. The mechanism is inviscid in nature and independent of the no-slip condition at the boundary. Although viscous diffusion acts immediately after generation to spread vorticity outward from boundaries. And of course, because of this revolutionary concept, the paper was rejected at the JFM. Makes perfect sense to someone like myself. I mean, whenever you come up with revolutionary concepts, or not revolutionary, but concepts that try to correct prevalent misconceptions, of course it will be rejected at the JFM. So that's understandable. That's okay. I mean, the community will push back, obviously, and so the paper did not gain traction. 1984 paper did not gain traction. It was published in some okay journal, but it's not the most prestigious journals. Until very recently, now we have series of papers in the JFM. This is just one of them. This is 2020, Stephen Terrington, The Generation and Conservation of Vorticity, saying exactly the same thing as Morton said, 40 years ago. And again, here is the abstract of the paper by Terrington et al. The only mechanism by which vorticity may be generated on an interface is the inviscid relative acceleration of fluid elements on each side of the interface due to pressure gradients of body forces. Viscous forces act to transfer circulation between the vortex sheet representing the interface slip velocity and the fluid interior, but do not create vorticity on the interface. All right. So what is the delta that we gained in here beyond Lighthill and Batchelor? independence of the no slip, because again I'm stressing, Lighthill and Batchelor, they said it's not viscosity. They didn't make it clear though. They didn't say it explicitly. I mean, you can deduce it clearly from their explanations, but they didn't say it explicitly. Here, they are saying it explicitly, and they are saying it's independent of the no slip, and they are saying it's the only mechanism. It's clear, crystal clear. And let's see why. So I'm going to demonstrate this by examples. Examples of fluid mechanics, actually presented in both papers by Morton and Terrington. And again, it's not just a single paper by Terrington, it's actually a series of papers. This is just one of them. So this is an impulsively started Couette flow. So we have a Couette flow here. So a flow in a channel, we have the upper wall is stationary, the lower wall is moving with speed u0, and we apply this u0 impulsively, all right? And we considered a very easy case, following back on Varon's question. This is again the very easy case that the type of problems that you get into 30B, where it's laminar, there is one component only in the x direction that depends on y, natural satisfying continuity, and you neglect the inertial term, so the only acting force is the viscous diffusion. So that's an extreme example. We're not talking about a high Reynolds number flow where it's the convection will dominate viscosity. No, here viscosity is the master, right? There is no other force. So let's see what do we get from this extreme example. The interesting part is that in this example we can get analytical solution. So here this is the no slip boundary condition at the lower wall, at the upper wall, and the initial condition, this should be u of y and 0. The initial condition is 0 everywhere. Luckily, like I said, we can get an analytical solution, which were presented in some efforts by also the same group of Terrington. So this is the velocity field normalized by the plate velocity, and this is the normalized vorticity. The green elements are the steady state solution, which you guys know for the Couette flow. And there are some transient terms. Lambda here are the eigenvalues. I mean, you can use 200B and 230B stuff to solve these kind of problems. It's not difficult at all. Of particular importance is the vorticity. So let's focus on the vorticity. And it's an analytical expression, you can go and play with it. It's a function of y and time. So you're gonna pick some time instance and plot this as a function of y. Here are the plots. So this is the y-axis, vertical axis. The x-axis is the omega, the vorticity, all right? Blue is one of the early moments. And then we progress in time, we get the red at a later moment, we get the yellow at a later moment, we get the purple, and we get the green almost steady state. So the steady state, as you can see from the green expression here, is just uniform vorticity distribution, one everywhere, all right? So what do we get? Let's look at these and what conclusions do we get from these plots? First, at any time, at any particular time, so pick a curve, pick any curve of these, the maximum omega occurs at the wall at y equals 0, right? And then, at the wall now, the maximum omega between times occurs at the early times, right? So now, let's consider this instant because it's important. At the early time, at the beginning, the impulsive start, at the wall, omega was infinite actually, a vortex sheet. This is in accordance with Lighthill and Batchelor and everyone. So what do we get from all this? The conclusion is all vorticity is generated at the wall at time t equals 0, at the beginning. In fact, this is the main conclusion of Morton and Terrington. All the vorticity is generated at the wall at time t equals 0. And let me show you more, and we'll come back to this. Here is the channel. The lower plate is moving with u0. Let's consider this contour that is made out of x excursion of infinitesimal width, delta x, and goes all the way to the channel, all right? We can talk about the circulation of this contour. So this is basically the total amount of vorticity, right, generated in the whole slice, okay? And because things are uniform with x, so it doesn't matter delta x. We can actually divide by. And if I divide gamma by delta x, we get our little gamma, right? Which is simply the integral of the vorticity across the vertical channel. Any question about that? And when we do this, when we use the analytical expression for little omega, plug it here and integrate with respect to y, we get a constant. So let me finish this, just finish this. So what does this mean? This is the total amount of circulation developed here. It's all developed at time t equals 0 by this amount, which is u0, independent of viscosity, in this purely viscous fluid, right? And this is independent of viscosity and it doesn't change whatsoever. At the beginning, this whole much vorticity was distributed over a zero thickness at the wall, giving infinite vorticity at the wall, zero otherwise. And what happens afterwards? Here are the figures. This vorticity generated at the wall by Inviscid mechanism is diffused outwards by viscosity. So here, after a while, you get this blue curve. Now the vorticity is distributed over a thin layer, only 0.1, but the rest is zero, no vorticity gone. Then you allow time to evolve. Let's look at the yellow. Now we have vorticity up to, let's say, 0.4. The rest is zero. The steady state solution, we diffuse all the vorticity, we get the green curve. Any question about that? Thomas?
What I'm still confused about is that if you have the no-slip condition to begin with, like, is that kind of implying that you need to have viscosity? Since
Yeah, I did not address the no-slip yet. Yes, but I'm addressing the effect of viscosity itself, like this viscous diffusion term and the quantitative effects of viscosity. The circulation developed is independent of viscosity. That's the, and this whole dynamics that the generation mechanism, the whole amount of vorticity generated, it all generated at the wall at time t equals 0 by an amount that is independent of viscosity. Then viscosity acts to transfer it to the interior of the fluid by diffusion. So that's the whole. Yeah, and your point is very well taken, because this analytical solution is obtained by applying the no-slip boundary condition. So that's the straw man here, is that, still have the no-slip boundary condition. So yes, viscosity as a quantity, as a quantitative effect, probably doesn't play a role, but a qualitative effect, it enables the no-slip boundary condition. So this I did not address yet. Any question about that? Yeah, Shatish.
So at t equals 0, y equals 0, omega is infinite, and then the viscosity acts too. So if I look at general fluid mechanics, incompressible, compressible. So let's say there is some edge velocity ue, and it's creating an infinite vortex shape. Now if I keep increasing the ue, basically now I'm saying that there is this concept of different strengths of infinities. So like if I keep increasing my edge velocity, does it start to affect my viscosity as we see in compressible flows? Like,
Does it what?
does it start to affect my viscosity as well?
What do you mean
Like-
affect your viscosity?
Like, let's say there was a solid boundary and suddenly I gave 50 meters per second, and there is a solid boundary and suddenly I gave 5,000 meters per second. So, but in the incompressible regime, we assume that viscosity is a constant, but in practicality,
Yeah,
it's
if it
not.
goes to practically, it may. I personally don't know, because things will heat up, and the effect of heat will affect viscosity, and. But yeah, could it? This is another. Yeah, this is another effect, but this same theory is still applicable. How far is it from reality? That's another question. Another example, similar example, impulsively started rotating cylinder. Why are we focusing on impulsively started things? Because the skeptical folks will come at this. No. Consider. Impulsively started, flows are not realistic. Let's do it gradual. Well, here is the issue. If you do it gradual, so you have continuous generation of vorticity, correct? Because here, the vorticity comes from where? After all this, comes from the boundary, from the tangential acceleration. You create a tangential acceleration in the boundary, you get vorticity generation. Period. That's it. All right? So when you do it impulsively, the moment of generation is very clear and distinct. If you do it gradually, then whenever you have changes, whenever you have acceleration, you get vorticity generation. So the vorticity generation will be continuous, right? And what will happen? Well, during these moments, diffusion is also acting. So you are generating vorticity at the wall, right, continuously, and viscosity is taking this vorticity continuously also into the fluid. So the d gamma dt here will have viscosity in it. But this is not because of the generation, it's because of the diffusion. So if you want to make it clear, separate them. In fact, this is why Morton suggested in these scenarios where he called slow generation of vorticity, if you want to separate generation of vorticity from the diffusion, go and kill the viscous still. In order to get the pure generation of vorticity, focus on the inviscid mechanism, because this is where the generation is happening. So in continuous acceleration, the picture is cluttered because we have simultaneous generation, inviscid, and diffusion, viscous. Abdel?
Yeah, but I think this apply only to the wall. But if I'm talking, okay, the wall is generating the vorticity and it's continuing with me. But I have more layers of fluid that is also generating because of the difference of relative velocity between them. And this will also create vorticity. And this vorticity might be because of viscosity.
I object to the wording.
Yeah, maybe wording. Yeah,
Let me see.
But can you get my point?
Yes, I get. Here. When this, let's talk about the yellow figure. Let's consider our yellow at point 2, high point 2, high point 1. That's clear. Yellow high point 1. That's a point. That's a fluid element here, and it has this much vorticity. It got it from where? From the fluid element below it, right? By diffusion. Now, here is the philosophical. It's not philosophical. Here is the real question. So this fluid element got this vorticity by viscous diffusion from the fluid element below it. Can we say that viscosity generated this vorticity?
But this point has a velocity now,
Yes.
because I'm not talking impulsively. So this point will have velocity. This velocity with the velocity of the wall will impact all the point.
Yeah, these are not generation. These are vorticity that's all generated before. That's the point. There is no interior generation of vorticity. It's vorticity that already generated before, and we can transfer it by viscous diffusion.
So in this curve, is the area under the curve constant or the steady?
Yes. Yeah, that's the area under the curve. That's the integral of omega dy.
I
Yeah.
mean, this is quite good.
Yeah, indeed, yes.
Proof that says whatever you have that's steady is related with.
Yeah, this is, exactly. When I see this is, this is crystal clear. I mean, that's the total amount of generated vorticity as a global quantity, right? The integral of vorticity, that's the total amount, and it's independent of time, and independent of viscosity. So it's, Thomas?
So with the viscosity, when it diffuses it would also have to destroy vorticity, right? Because you don't always have infinite vorticity.
Yeah. This way it prevents it from staying infinite at the wall. It smears it out. Yeah, immediately.
If you were sum all of it, it would be infinite, right? At a later time.
No, if I sum, I think the next example will clarify this. But here, when we sum all of them, we get a finite number. That's the summation of all vorticity. We get a finite number. The issue is that this finite number was distributed over a zero thickness at the beginning. So we get infinity only at the beginning. Yeah. Cody, you wanted to say something?
It sounds like confusing the terms between the vorticity and the density of the vorticity is not spread through.
Yes, I'm actually coming back to this. Yeah, because that's one of the main sources of confusion. But let me give this other example quickly. This is impulsively starting rotating cylinder. Again, we're considering the very easy case where viscosity is the only player. Right? There is no convection term here. And again, we can do analytical solution. Here, this is the no-slip boundary condition at the wall, far field, and the same mistake here. This should be U of R and 0. The initial condition is 0 everywhere. U here is representing the tangential velocity. We have just pure tangential flow as a function of the radial R. We have an analytical solution. We can look up the transient terms in one of the textbooks. And it's the exact same scenario. At any moment in time, the maximum omega occurs at the wall. And at the wall, the maximum omega occurs at the initial time due to the impulsive start. And at the wall, at the impulsive start, omega is actually infinite. It's a vortex sheet created at the impulsive start. So all this, again, lead to the same conclusion. All vorticity is generated at the wall at time t equals 0. And when we do the same global measure, let's sum all the vorticity in the entire domain, from r to infinity, 0 to 2 pi, r to r theta. All right? And we have the analytical solution here for omega. We just plug it here and get the integral. We simply get this value, independent of time again, independent of viscosity. That's the total amount of generated vorticity in the domain in a purely viscous fluid. All right? Any question about that? So this, indeed, the vorticity generation mechanism is purely inviscid. In my opinion, there should not be really debate about this. Not the other way around. It's not like, oh my goodness, this is 77% believe that it's viscous. That's an unfortunate misconception, because vorticity generation mechanism is one of the most important mechanisms in fluid mechanics. So to have the overwhelming majority of the community, having misconception about it is not a good outcome. But anyway, thanks to these efforts by Morton and Terrington, some of them are very recent. We're talking about 2020 papers in GFM. So it may not, they did not get enough time to be spread within the community. Here I'm coming back to the main concept that you guys alluded to, Cody, Thomas. This is a very important distinction that is probably causing the main confusion, actually. There is a fundamental difference between vorticity, omega, as a rotationality of a fluid element. The fluid element is really rotating by this, all right? Versus gamma, right, which is an integral measure of this omega. But gamma can be, simply a jump or a discontinuity of tangential velocity, right? The former quantity, little omega, of a fluid element, really a fluid element cannot acquire rotationality in an incompressible flow without viscosity. Yeah, I completely agree, of course. So again, a fluid element cannot acquire rotation in an incompressible flow without viscosity. And this is why the proponents of the viscous mechanism, they rely on this. Yes, indeed. But remember, this one, the jump of tangential velocity, that's purely inviscid. This is what we showed. Moreover, the original source of this rotationality, so yes, we get this rotationality by viscosity, but the original source of it came from where? It must come from a jump at the wall by purely inviscid mechanism. All right? Any question about that? Still did not address the no-slip boundary condition. So let's go. So for this, actually, Terrington, in this paper, he did the following nice discussion. This was his main schematic diagram. So two fluids, fluid 1 at the bottom, fluid 2 at the top, separated by a sheet here or an interface, what you call interface. One of them can be solid, by the way. So his demonstration accounts for also these cases where one of them can be solid. So we have a fluid over a solid kind of thing. And he considered the total circulation of this contour, the outer contour. So this is these are three contributions. One from summation of omega in fluid 1, summation of omega in fluid 2, and the jump across the interface, right? And then he managed in equation 2.2 in the paper to derive an equation using Navier-Stokes equation, the no penetration boundary condition. He managed to derive an equation for d gamma by dt of this contour, and he found it to be independent of the tangential boundary condition, whether it's no slip or not. So basically, he did not need the no slip boundary condition to obtain the d gamma by dt. So, and to elaborate that, he considered three cases, very interesting. If we have no slip boundary condition between the two fluids, so no relative speed, right? No relative tangential speed, so gamma must be zero, right? The jump must be zero. So all gamma generated by inviscid relative acceleration must go in the fluid interior to satisfy the no slip boundary condition. And it goes into the fluid interior by viscous diffusion, of course. So this is why viscous diffusion is linked to the no slip boundary condition. If you want to enforce the no slip boundary condition, so all gamma must go away, you need viscosity to take this gamma to the interior, all right? But now he changed the boundary condition, the tangential boundary condition. He didn't enforce the no slip. He enforced the free surface, what we call free surface. What is this free surface? Like zero shear stress. Then in this case, not all gamma will go into the fluid interior. Some gamma will remain to satisfy the required boundary condition. And likewise, if you have free slip, all the gamma will stay. Why? Because you don't have a mechanism to take this gamma into the fluid interior. But in the three cases, the d gamma dt is exactly the same. It's independent of the tangential boundary condition. Whatever tangential boundary condition you have, it's the total d gamma by dt is the same. All what the tangential boundary condition does is that it dictates how much circulation remains on the surface and how much goes into the interior. All right? And this actually now explains, Abdel, you wanna? No. This explains these computational simulations. If you go on OpenHirsch, numerical computation of internal and external flows, volume 2, section 19.4. Let's read together. It appeared that computations based on the Euler equations and which did not implement any form of Couette condition still produced accurate results of circulation. This has been confirmed since then by many computations on two-dimensional as well as three-dimensional airfoils and wings. And then he added, this remarkable result implies the existence of some mechanism, because it's not the Couette condition and it's not the no slip boundary condition, they are simulating pure Euler. Some mechanism which reproduces and simulates the essential physical phenomena leading to the generation of circulation and lift. So these are pure Euler simulations, no slip boundary condition, so there is slip on the boundary, no viscosity, and they found circulation and lift just fine, and without even the Couette condition, all right? And of course, they invoked, there seemed to be some mechanism. Can you imagine what mechanism came to their mind? Because of this preoccupation with viscosity, but there is no viscosity, this term of the Laplacian is not there. And there is no slip boundary condition. There is no boundary layer. What mechanism could have come to their mind? He said, okay, wait a minute. The numerical algorithm has some numerical dissipation. So this dissipation plays the role of a viscosity to enable this. This is just preoccupation with this mindset of viscosity. And even if true, remember, even if true, there is no boundary layer here. There is no slip boundary condition. They did not enforce the no slip boundary condition. And they were not the only ones. Like I said, there are many. I'll give you another example. There are many really, but I highly recommend that people go and read this paper. And these folks, when they proposed their work in circa 2010, like 15 years ago, not too long ago, it was rejected even at the IAA. So again, the community rejected their work. It's like, oh, this is crap. The title of the paper is very attractive, Resolution of Damp Paradox. So let's read together. We find by computational solution of the Euler equations with slip boundary conditions, no enforcement of the no slip, that the potential solution develops into a turbulent solution with substantial drag and lift. We thus obtain, without any presence of viscous boundary layers, substantial drag and lift in accordance with the observations and the conjecture of the curve. Another paragraph. In particular, we show in this reference that drag and lift of a car or airplane can be accurately predicted by computing turbulent solutions of the Euler equations with slip boundary conditions without resolving thin boundary layers. This is by fluid dynamics expertise considered to be impossible. And there are several simulations. I will not have time to discuss them all. But actually, I personally, from a mathematical perspective, I see these particular, by the way, these simulations by Huffman and Johnson, the type of simulations were very different than those by Ritzy. Very different types of simulations. I like these ones so much, by the way, Huffman and Johnson. And I view them mathematically as weak solutions of Euler. So let's discuss this. Let's discuss why this problem is related to the convergence of Navier-Stokes to Euler. So this is Navier-Stokes. New here is the viscosity. This is the damn term. So viscosity, and I had subscript in for a sequence. So we're going to take a sequence of viscosity. So we start with viscosity 100, 10, 1, half, 0.1, 10 to the power negative 6, 10 to the power negative 12, and so on. So, okay, a sequence of viscosity. And for each value of viscosity, let's hope that we can solve the Navier-Stokes equation. Right? And we get the viscous solution. This is the U sub n here. On the other hand, we have Euler equation, no viscous term at all, and let's denote it by U sub 0, right? The question is, as I said, the sequence of viscosity I told you about is actually converging to 0, right? Smaller and smaller. The question is, as this sequence of viscosity converges to 0, does the corresponding sequence of viscous solutions of Navier-Stokes converge to that of Euler? That's the question. This is an open problem in mathematics, which is cousin to the other open problem of the millennium problem, existence of solutions of Navier-Stokes. At the outset, you may see this as a fancy abstract math problem, which indeed it is. It's not easy at all. But in fact, it has very serious implications. Why? Because in all these serious applications, airplanes, race cars, submarines, wind turbines, you name it, these are high Reynolds number applications, and engineers in these applications, they perform in their routinely daily tasks computational simulations of Navier-Stokes, right? But as you guys know, these are all very high Reynolds number flows. So the most powerful supercomputer on the planet will not be able to solve Navier-Stokes equations in these scenarios. So there is a bad need to develop approximate solutions. If we cannot get the solutions, at least we get approximate solutions of Navier-Stokes at high Reynolds numbers, right? From systematic ways, not in an ad hoc way like what is done now in industry. If this convergence holds, it would imply the following, that the solutions at infinite Reynolds number of Euler should be reasonable approximations to the solutions at a finite but high Reynolds number. The difference would be order epsilon, or 1 over Reynolds number, 1 over square Reynolds number. So this convergence problem actually, it has very serious implications. Of course, anyone can think of counterexamples. Like what? Here is a candidate counterexample. What do you mean counterexample for where we have Navier-Stokes does not converge to Euler? Euler gives you something completely different, right? So this is separating flow over a cylinder. At higher Reynolds number, we know that the flow separates from the cylinder, creating some wake. And on the other hand, the solution that we teach in the undergrad is attached flow. So all Euler solutions here will not give you a separating solution like this. So why are you saying that it's an open problem? Because what does it mean, an open problem? An open problem is waiting for either a proof or disproof. The disproof should be easy because you just need a single counterexample. I'll tell you why this is not a counterexample, and before that I'll tell you more about Euler equation, right? As you guys know, in Euler equation the energy is conserved, right? Circulation is conserved. We studied so well in this class. Vorticity is conserved, helicity is conserved. So this is why probably in the mindset of many fluid mechanicians, they look down at Euler equation because it's not rich enough to capture, real behaviors like dissipative flows and, lifting flows. Energy is conserved, circulation is conserved, and so on, right? The interesting point is that all these conservation laws valid only for classical and smooth solutions. Once you open the space for weak solutions, discontinuous solutions, then none of these actually holds. What do you mean discontinuous? Because look here, and that's the interesting point. If I'm looking here and I want Euler to predict this, this is actually a shear layer, right? From a viscous solution, that's a shear layer. At very high Reynolds number, the thickness will go to 0. So what will I get? I will get discontinuity between the outer and the wake. So I'm looking for a discontinuous solution to begin with. If I don't consider discontinuous solution, so that's actually, I'm looking into the wrong space. So this takes us to the concept of weak solution. I'll give a little bit of background about weak solutions. And I like this example because it sets the mindset. If I ask you, this is so simple now. Let's tone it down. It's so simple. We're talking about just 1D algebraic equation. If I ask you, how many solutions do we have here? What are the solutions of this equation? If you are before 1500s, so that's before complex numbers, you only know about real numbers, you've never seen anything other than real numbers, you will say with full confidence and certainty that this equation has only one solution, right? And then later on, thanks to many people, including Gauss, we became very familiar with complex numbers. We now know that this equation has more solutions, has 3 solutions, right? So indeed, whenever you open the space of solutions where you do your search, it's probable that you will find more solutions, right? So the same thing here, if you have an ODE or a PDE, it doesn't matter, right? And if I ask you, can you find a solution to this equation? You said, yeah, sure. If we are before the 1940s, where all what we know about is just smooth functions, which means that for a function u to be a solution of this equation, I need to get the value at some point, the derivative at the same point. To evaluate the left-hand side, they must be equal the right-hand side at the same point. And this equality must hold for all points. So the function and the derivative must be defined for all points, right? So we're talking about smooth functions. Now we want to expand this a little bit. So after Schwartz's theory of generalized functions, or what they call distributions, now we can allow for discontinuous, because remember, the physical solution was discontinuous. I'm looking for discontinuous functions. But how can I make sense of discontinuous functions to be a solution of this ODE or PDE if the derivative is not even defined, right? So that's the issue. So this is why mathematician came up with this trick. He said, yeah, no worries. Multiply both sides by test function phi and integrate. And once you do this, what was the term that was causing all the problems? Well, it's the derivative. Fine, now it's multiplying by a smooth function phi. Let's integrate by parts, because when you integrate by parts, you shift the derivative to the other function, right? But you pick up a boundary term. No worries, let's kill our boundary by requiring that this function phi to vanish at the boundaries. So at the end, you get this equation, right? So now we will say a function to be a weak solution of the original differential equation, it must satisfy this for any smooth function that vanishes at the boundary, right? And if you look at this equation, it doesn't require your main function u to be differentiable, right? So you can have perfectly discontinuous functions here. So this is just of course there are a whole math behind it. I mean, this is just a cartoon example, okay? But now when we go and look at Euler equations with this lenses of weak solutions, things are extremely different from the picture that we are used to in grad school. And I really commend the great efforts by Greg Eink over the last 2 decades. So these are also relatively recent. He wrote on how Euler equations can be dissipative, and how they can resolve D'Alembert paradox, how can they produce drag. All these efforts, they culminated in a 70-page paper in the GFM last year. GFM perspective, I don't think they would allow him to publish it as a regular GFM paper because it's too much disruptive. So it's GFM perspective. He's offering his perspective. So it's a different perspective than the majority of what the majority of the community hold. So let me show you some exhibits here. Quickly, it may be less commonly appreciated that singular or weak solutions of the incompressible Euler equations are a good candidate to describe turbulent flow in the asymptotic limit as Reynolds number goes to infinity. In fact, as first conjectured by Onsager. So Onsager was a Nobel laureate, chemist, was interested in fluid mechanics at one point in his career, and he wrote one paper in fluid mechanics. This is the paper in which he wrote, turbulent dissipation could take place without viscosity. In the absence of viscosity, the standard proof of conservation of energy does not apply because the velocity field does not remain differentiable. So that's the point. We usually take the fact that Euler is conservative as, for granted, because there is no viscosity, there is no dissipation. It's conservative, right? Yes, but if you look carefully at the mathematical proof of the conservation of energy, you will find that it requires differentiability. So if your solution is not differentiable, if it's not even discontinuous, then yeah, there is no guarantee. And in fact, this is less known in the fluid mechanics community, but it's very well known in the math community. That was not the issue at all. The issue was, what is the limit of smoothness below which Euler would not conserve energy? And this was conjectured by Onsager. So when Onsager wrote this was not debatable. That's okay. What is the limit below which Euler is conservative, above which Euler is guaranteed to be conservative? So he said if the velocity is Holder continuous with exponent less than 1/3, energy conservation is no longer guaranteed. What do we mean by Holder continuous exponent 1/3? Holder continuity is a measure of continuity between the regular continuity and differentiability. All right? So if the function is not differentiable, it's not smooth, okay, how less smooth or how continuous it is. So let me give you examples. So the purple function here is like x squared. That's smooth and everything is nice, differentiable. The yellow is just absolute value of x, okay? So this is Holder continuous with exponent 1. We call it Lipschitz. So the red is just square root x kind of thing. This is Holder continuous with exponent 1/2 and so and so. So the limit as conjectured by Onsager is the 1/3. And this was just a conjecture. Nobody knows whether it's true or not. Very recently, so these stuff are recent. We're talking about a few years ago. Philip Essett, one of the finest mathematicians, he provided a rigorous proof of Onsager's conjecture. What does it mean? It means that if really the velocity field is less smooth, mathematicians say less regular, then this energy will not be conserved. And he constructed these examples. So he started with some initial conditions that is rough, and he let it evolve under Euler dynamics as a weak solution, and after some finite time, the solution became the zero function everywhere. The entire initial kinetic energy was completely dissipated. So the conclusion here is that Euler equation can give you dissipative solutions. All right, it can dissipate. We are not talking about limit as viscosity going to zero. We are talking about purely Inviscid solutions of Euler, but in the weak sense. All right? Greg Eying provided a similar limit on smoothness for Kelvin theorem to hold, in fact, a higher limit. And in a more recent paper, he wrote this: the drag on the body in the infinite reduced number limit can be computed entirely from the limiting weak Euler solution without the need to resolve small viscous length at the wall. You don't need boundary layer to get drag and these kind of things. Of course, talk about pressure drag, which highly dominates at very high reduced number. I think all this can be maybe summarized in this statement. Under very modest assumptions, the viscous Navier-Stokes solution must tend in the limit as reduced number goes to infinity to a weak solution of the incompressible order. So basically, the conclusion is weak solutions of Euler are very rich. They can dissipate energy, they can generate circulation and lift, they can give you drag, they can give you whatever, all right? Let me quickly go back to the pioneers and view their characterization with these lenses of weak solutions. This is Prandtl paper, Wright Memorial Lecture, where he received the gold medal from the Royal Aeronautical Society. And he wrote this famous quote that I used to quote all the time: every confluence at sharp edges can, without contradicting Kelvin's theorem, give rise to a surface distribution of vorticity, a vortex sheet. So this is basically the picture. So at the beginning, at the impulsive start, the confluence at the sharp edge will give rise to a sheet of discontinuity. And because of this discontinuity, we have, vorticity generation here that is purely inviscid. So Prandtl was saying a discontinuous distribution of velocity is set up, which effectively constitutes a sheet of intense vorticity. The surface of discontinuity then begins to roll up into a spiral. Of course, the gamma dot, as you guys derived it in this class, has nothing to do with viscosity. It's just the difference between the two speeds. Again, like going with all the spirit of this lecture. And then he moved to this. The last slide was Prandtl discussing how lift and circulation can develop in a purely inviscid fluid. Then he said, okay, let me now move to a fluid with small but finite viscosity. How the picture would be different. And he is discussing. He's saying, we can now see that layers of very small but finite thickness plays the same part which we have already ascribed in the previous section to the surfaces of confluence. We now have layers of vorticity instead of surfaces of vorticity. That's the only difference. All the rule of viscosity is that it smears out this sheet of discontinuity into a finite layer. But the total amount is the same. So he is saying this difference between the two pictures affects but slightly the general behavior of the fluid, so that no serious error will be made if in the case of flow behind sharp edges, viscosity is totally neglected. In the two cases, you will get the same amount of circulation development. And these are the words I'm quoting. These are the words of Prandtl in one of the most famous papers. Again, the prevalent convection of the community is not justified in my view. And he's saying, we thus get the unique characteristic that it's precisely these turbulent flows of low resistance around bodies which can be so closely represented by the theory of the perfect flow. So this picture, I think what Prandtl was missing, or what was not available to Prandtl to make his stance stronger, is the concept of weak solutions. I think if he was aware of the concept of weak solution, it came well after him, unfortunately, he could have simply described this as a perfectly legitimate mathematical weak solution of Euler. And this phrase could have made impact on the stance of the British school, because they were school of mathematical physics. Wagner, I mean, there is no time, but we actually, Kshitij translated this with the help of ChatGPT. But I wanna, so you can read this later. And following in this paragraph, he had a separate paragraph with italic for this statement. Therefore, we do not need to invoke viscosity in order to explain the emergence of lift on a body of this kind. And then you can continue that this is, perfectly fine with the fundamental principles of ideal fluid. So conclusions. The vorticity generation mechanism at the wall is inviscid and is independent of the no-slip boundary condition. I believe that every student in fluid mechanics should be aware, of this concept and this description. Thanks to Morton and Terrington and others. Proper CFD simulations of Euler's equations without enforcing the no-slip, they are very rich and can result in lift, drag, and separation. In fact, the industry has relied on it for a long time. And these solutions are viewed as inviscid limits of the Navier-Stokes equation. Why I'm saying inviscid limits? Because of the numerical dissipation thing. It's as if you're taking viscosity to zero. On the other hand, weak solutions of Euler's are very rich. They can be turbulent, dissipative, lift generating, drag generating, whatever. Prandtl's demonstrations and Wagner's solution of the circulation development are best viewed as weak solutions of Euler because they are discontinuous solutions. The open problem is the weak solutions of Euler are non-unique. So we're not sure which one nature picks. So we need a selection criterion. This is why in our lab, we really believe in the value of the principle of minimum pressure gradient as a promising selection criterion. Any question?
It's not like entirely related, but since I am also taking a course in turbulence at the moment, I recently read that the cascade phenomenon. So we have energy feeding using some forcing or mean shear. We have dissipation using viscous scales, but something that I have not read log, but it has been written at multiple places, that the cascading 3D from larger scales to smaller scales is purely governed by Inviscid processes.
That's right, yeah. And
So-
Professor Johnson, he stated clearly in his presentation, yeah.
So
Yes.
So why doesn't the community, like, did someone try to explain that using viscosity or?
I gave you the whole history, so it's it's a bit surprising when you see it after the fact. No, I mean seriously, I mean, if you see how people when I just even bring this up, they come and shout and attack. It's like, oh, this is taboo. It's what are you talking about? And from my perspective, this is actually crystal clear. What are you talking about? But it's sad, Cody.
You feel like some of the terms may be overloaded because you have rotationality as a fluid particle, you have circulation over a multiply connected space, and they're not physically the same thing. A vortex sheet contains nowhere a rotating particle. You can put
Yes,
an object in
yes,
there and it
yes.
will not rotate an object.
Fully agree.
So that there's a kind of an overuse of the word that's kind of overloaded.
Yes.
So that's part of the confusion too.
Yeah. And also, yeah, something I forgot to mention. So this is why I'm saying this, because from discussion with many people of the other background, this was an important point. When they thought about it, they were open to reconsider things. Another point that really made an impact in the discussions is the following. Yes, here. So if you focus, let's say the upper fluid is a fluid and the lower part is solid. If you're just focusing only on the fluid, which is the upper part, and not seeing anything from the solid part, the only piece of information, the only way to know about what is the solids doing is by the no-slip boundary condition. This is why they care about much. But when you consider them combined, you don't need the no-slip boundary condition. That's the point, all right? So this is the trick that Terrington did. So nature knows that there is a solid and fluid, so then knows that there is, two entities. But if you think of from the mindset of a pure fluid mechanician doing computation on the fluid domain, doesn't care about the solid body at all, the only way he or she gets piece of information is through the no-slip, and of course the no penetration. The no penetration is much more important. All right, so this is also, it made a difference in the discussion. When we consider both of them, yes, it makes sense that, I don't need the no-slip boundary. I don't need the tangential boundary condition between the two domains anyway. All right, folks, thank you so much. I'll see you Monday. Right, Monday?